So, welcome to the second of two videos on chapter 1 of the Guinn text, the chapter where we establish the rules and the parameters of the mathematics we do in this course. So, in this second half, I'm going to be talking about something called significant figures. And this is a straightforward but can be complicated idea. So the idea is that you want to, as a researcher or a scientist or a clinician, tell your reader how accurate your toy is. So I could measure this floor with a laser guided pointer that could measure it to micrometers. I could measure it with a meter stick, and then basically I could guess it to millimeters, or I could take, this pen and measure it in pens and guess how long the pen is. Let's say I think it's 10 centimeters. So I'd measure it as 12 of those 120 centimeters. I'm totally guessing, right? So here's a cup of coffee. Let's say it has 400 milliliters in it. Do I know it has 400 milliliters? If you were asked me, I'd say, about 400 milliliters. But I'm guessing at every number, including the 4, right? If you ask me how far it is to New York, I guess, 250 miles. I'm guessing 2 significant figures. But the 0, I have no idea. I'm guessing at the 5. I'm really guessing at the 2. So this is about measured zeros and guesstimated zeros, right? So if you said, how many people go to USM? And someone said, well, it's 6,000. Only the 6 is even meaningful at all, and it's a guess itself. You could only say that one number, that 6, was significant, right? So what did I just do? I guessed 400 milliliters. What am I saying? I know it's about 4, but I'm guessing it could be 350, it could be 450, it could be 500, right? So it's all your measured numbers, and the first one you can guess at. So, how many feet is it across campus at USM? 10,000. Only that one is measured at all. It's a guesstimate, right? There's only one significant figure. Now, I could have measured my coffee cup or measured some out into a measuring cup, in which case I could have a measured number. Let's say I took some of that and poured it carefully into a measuring cylinder, a graduated, meaning it has lines on it, graduated cylinder. I could say with some accuracy what, let's say, 40 milliliters look like. How would I say to your reader that 0 is now a measured 0? Well, I could put a decimal. Notice that decimal. That decimal right there indicates that both of these are well-known numbers. So while this has one significant figure, this one now has 2. Because I'm saying by that decimal point, both the 4 and the 0 are measured. What if I took a very, very accurate glass hand-blown pipette, and I withdrew 4 milliliters of coffee from that so accurately that I could say down to millimeters how much coffee I withdrew? And in fact, I withdrew 4 and then like 0.00 milliliters. I measured down to that very small volume, micrometers, right? Because this is 4 milliliters. Those are micrometers. Why would I write those zeros if I didn't measure them? I'm bragging. They're hanging off the end there after the decimal. And they're there to tell you about how good my tool was. So there is 3 significant figures. So what generally is the rules of significant figures? Well, first of all, any non-zero number is, of course, a measured or guesstimated number. So if it's not 0, it's in. It's a significant figure. Now, if a 0 is between 2 non-zeros, for instance, this one here, well, that couldn't be any other number. If that's a 4, that's got to be a 0 in the tens place. So that's 3 significant figures as well. So that one must be significant. All these 3 must be significant. So only when it comes to zeros does it get complicated. In the case of zeros, there's this question of where it's oriented. Where's that 0 located? If it's closest to the decimal point, it often is not significant. Remember that these 2 are not measured. They're just placeholders to tell you how big, right? If I did the math to convert that to liters, I would get 0.4 liters, and only that number is significant. It's only one significant figure. Significant figures don't go away if you change the unit. So those zeros couldn't have been meaningful. And by the way, this gets dense. You need to read the text and really understand this, or go to YouTube, look up a significant figures discussion and have someone else explain it. Please do. And in all these topics, there is YouTube videos and web pages, all this host of information you should take advantage of. Now, we know this one has 3 significant figures because that 0 is between 2 measured zeros. What about that one? Well, the rule's the same as the ones we were just describing, in that, why would I write that if I didn't have a tool that could measure down to that number? In other words, that must be a measured 0. And because it's a measured 0, it's in. So this is also a measured 0. So that has 4 significant figures. So what about this one? Well, that 0 is just there because it's a convention. It never counts. That's a non-zero, and that's a measured 0. So this one, right, measured, because why would you write that 0 if you didn't have a tool that could measure down to, the tens place on microliters? So that's got 2. Here's the more complicated example of this. You and I both look at this number, this one, and we say, well, if that's 1, 0, those are exactly 0. Surely those are measured zeros. They're 0, right? They couldn't be any other value. They couldn't be 5. They have to be 0. If they're 5, you would tell me they were 5. If I could measure that 1 down there, I could surely tell the difference between 0 and 5, right? So those are measured zeros, right? But no, they're not. If they're closest to the decimal, they are the same as these ones closest to the decimal. All that they are is placeholders. They tell you you probably picked a bad unit. If I change this number to micrometers, I would go 1, 2, 3. I would end up with 0.1 micrometers, right? So now I only have 1 measured 0. In other words, those are not measured zeros. This Remember, that's a measured zero. It's hanging up the end. That can only have two significant figures, as weird as that sounds. In this case, I have a zero between two numbers. That must be a measured zero. It must be significant. And these, well, they're dangling off the end again, so those must be significant. So in this case, all five of these are significant figures. What about this one? Here's the extreme of this example. You think, well, if that's a 6, those have to be exactly 0, right? But I'm here to tell you that these are placeholders because you picked a bad unit. If you picked nanoliters, you would come 6 decimal places back and the zeros would go away. And significant figures are immutable. They don't change depending on the unit you pick. So none of these are significant, only these. Remember, that's once again a measured 0 off the band. Only those are measured, so that's 3. So what is a significant figure? Well, you have to look at this image again, watch this video again, look at these examples from the PowerPoint. Be aware of the idea of infinitely significant, otherwise known as exact numbers. So how many summers have I taught an online course? 1. You think, is that one significant figure? No, it's infinitely true. It's 1 infinite, right? How many sticks of gum in a pack of gum? Let's say there are 8. That's infinitely true. Exact numbers should not limit you. And these are often a description of frequency, right? So if I say that I come to school 5 times a week, that's 5 infinitely true. So let's talk about, now that we have this idea of significant figures, let's talk about how we use them to do mathematics. So I want you to separate in your mind 2 ideas. One is when you add and subtract significant figures, and the other is when you multiply them. And on the quiz on Friday, I will definitely make you do both of these, add and subtract and multiply and divide. So let's first talk about adding and subtracting. So what you have here is 2 people who have measured things, and we're going to add these numbers up. Now, what's important to know is that this person had a really good tool. Look, they got down to not only millimeters, but down to micrometers. Whereas this person, well, 1.2, let's make it meters. Let's not be clever. This person only measured to, centimeters. In other words, all this accuracy doesn't mean anything because when you add it to this person's inaccurate measurement, what's the point of all that accuracy? So when you add or subtract, put them over each other, and you can only report the numbers that exist in both numbers. So what I mean is, so there's the math problem. But how many significant figures can I report? Well, because this person used such a bad tool, I don't know what these are. This could be 1.28 for all he knows. It could be 1.16. So I don't know what these are. In other words, none of these matter. And the answer can only be these two. So when you add or subtract, you can only compare to the extent that you go to the right of the decimal point. And I'm afraid that limits you, right? You could have 201.6023579, and that's 11.21. Now, what will be the answer? Well, I can't compare. I might want to add them up together. Right, so 9, 7, 5, 3, 2, 1, 8, 2, 1, 2. But at the end of the day, what you'll report is only this, because I don't know anything here. So what are these numbers good for? Nothing. Right, so 212.81 is all I can report. This applies to subtraction as well. So when you add or subtract, line up the decimal, make sure the units are the same. You know, you may have to convert, as I was about to do here, centimeters to meters to get them to be the same unit. And then you can only be as accurate as your worst tool. If one person is very accurate, one person is not accurate, your answer is not accurate. So adding and subtracting, line up the decimals, do the math, watch out to round up if it's a 5 or above, and then eliminate numbers you can compare. Now it's easier when you multiply or divide. And this is nice because when you multiply or divide, the rules make sense. The rule is you can only have as many significant figures as your least number of significant figures, right? So how many significant figures is my answer going to have? Well, whichever one has less. In the case of multiplication and division, this has 3, this has 3, 6. So my answer is going to have 3 significant figures. So here's some crazy math problem. What is the number of significant figures I can report? Well, in the case of multiplication and division, whichever number has less significant figures is what I can report. This has what, 2, 4, 6, 7. This has 4. My answer can have 4. And that's straightforward, which I appreciate. So look up practice problems, do the homework, try more of these. I'm limited in my ability, frankly, to teach this. I can only give you examples, and then you need to practice. You need to understand and absorb the rules, and ask me questions. Come to the Zoom meeting on Tuesday or Thursday and ask me questions. I will be doing examples of addition and subtraction and of significant figures, multiplication and division of significant figures. So come ask me questions. So last topic. The last topic is our metric unit of temperature. And I want you to know that the metric unit of temperature is not Fahrenheit. Only we use Fahrenheit. It's an embarrassing, frankly, strange, aberrant thing that you and I think of temperature in a Fahrenheit scale that no one else in the world uses. In Canada above us and in Mexico below us, On a hot summer's day, it is 25 degrees, or 30 on a very hot day. So we will go away from Fahrenheit, if only because it's a totally nuts, illogical scale that no one understands how it got adopted. Maybe it's more precise in that it has more digits per distance of temperature, but it's so poorly organized. I mean, 212 is the boiling point of water. 32 is the freezing point of water. When you step back and think about it, what? You know, even the body temperature is poorly designed. Herr Fahrenheit meant for the body temperature to be 100, and because he got it wrong, had a cold, had a fever, when he meant what he described as 100 is now 98.6 or lower these days. So we will use Celsius. And Celsius is so logical that I want you, now I'm not, some teachers would make you memorize 5/9 minus 32, some mathematics. I don't want you to do that because that doesn't mean you own it. I want you to own this relationship. What I want you to know is a couple of touch points, and then from there you can guesstimate. So here are my significant figures. So this is freezing point of water, body temperature, and here's the melting point of water. Or not freezing and melting, boiling point of water. Right, so this is solid to liquid and liquid to solid. This is gas to liquid or liquid to gas. Same idea. Now in Fahrenheit, we know what these numbers are. The freezing point or the melting point of water is 32. Body temperature is 98. And boiling point is 212. I would prefer, well, I'll never use those numbers, and we can't do math with that. No one does math with that. The metric unit of temperature, the way we describe heat, is in Celsius. So what is Celsius? Well, it's a logical scale. Monsieur Celsius said, let's pick out two logical points, freezing point of water, boiling point of water. Call those our parameters, make the lines in between that so it's 100 decimalized, and then everything is logical. Here Celsius said, well, that makes sense, right? Call that boiling point or melting point of water. Call that the point at which water condenses or boils. There's a logical scale. And that's the scale we'll use. That's the units of temperature we will use. We will never use imperial units. Now, if you use this scale, it turns out 98, 37 degrees Celsius. And if you remember these three numbers, you have a good grasp. You know, a very hot day, a day we never get in Maine, of 100 degrees is about 37, 38 degrees. You know, with that idea, you can describe a spring day of 70 degrees as, you know, 19 Celsius. So, you know, room temperature, 18, 19, 20 degrees is pretty typical. But I want you to know this set of parameters. Now, there is, beyond Herr Fahrenheit's crazy scale that we'll ignore in this course, other than, by the way, I'll ask you for these numbers on the quiz on Friday. So you have to know all 6 of these. But there's one more scale, and here's your problem. The problem was Monsieur Celsius, his scale for temperature made so much sense. Of course, you pick out 2 points, 0 and 100, and you make gradations between them. And that's how you do temperature. Here's your problem. Let's say you're doing a math problem about you have a balloon and you know the volume of it, you know the temperature in the room, and you know the room's at 1 atmosphere of pressure, and you put it in a freezer at 0 degrees. And you all know that if you put a balloon in a freezer, it gets smaller. We can do that math. You're going to do that math. But how much does it go down? Well, you set up the mathematics and then you realize that the temperature at the end was 0 degrees. And you say, wait, all my math just exploded because you can't multiply by 0 or divide by 0. The math makes no sense. So what happens? You have to have a new 0. You can't have 0 in mathematics. So all the scientists, and you and I are budding scientists, we need a different 0. So an Englishman who was named Lord Kelvin, because only the aristocrats apparently did science back then, Lord Kelvin said, hey, listen, if I plot the Celsius scale, there's another 0. There's a conceptual 0, this temperature that must exist where everything on Earth, everything in the galaxy stops moving. No energy, that a material would have no energy. And he kind of plotted it back, plotted back. If this is 0 degrees Celsius, he wanted to plot back to this place where everything stopped, right? Here's 0 degrees Celsius. Things are moving around, but here everything stops. Everything stops moving. And at this point, which became known as absolute 0, an absolute 0, he said, let's call that 0. So Kelvin picked out a number that he called 0K. You'll notice it doesn't have a 0 sign. It's OK. 0K. That's absolute 0. Interesting idea, which is that one of the laws of thermodynamics is you can't actually reach this number. You can get so close, but you can't get there. And since Kelvin didn't want to throw away the system, he said, I'm going to use Celsius's system, but I'm going to call this 0. And it turns out that if you track back from 0 Celsius back to here, you're at minus 273. So 0K right? Sorry. Minus 273. Better way to describe this is whatever the Celsius is plus 273 equals K. Meaning, if that's minus 273, and you come up to there, K is 273. If it's 0 plus 273, that's Kelvin. In other words, whatever the Celsius is, you add 273 to get Kelvin. I think I'm doing this badly. But whatever the Kelvin is, you subtract 273. So what really matters is Kelvin is 273 more. And you do need to memorize that number. 0 degrees Celsius plus 273 is Kelvin. So 0 plus 273 is the Kelvin temperature of the freezing point of water. 37 plus 273, you always insert it there, is 310 Kelvin. Well, 100 plus 273 is 373. And you think, well, why is he making us memorize these stupid numbers? Why 273 plus whatever the Celsius is? Because in terms of doing mathematics, we're going to need that number to be able to do a lot of what we have coming down the pike. You do need to know Lord Kelvin's scale, which says that whatever the Celsius is, just add 273. If it's, you know, -4 Celsius, -4 plus 273 is Kelvin, which would be 269 Kelvin. So you do need to know that scale. So imminently, you will find not just these 2 chapter 1 videos, but you will find more than one video on chapter 2. Chapter 2 is a discussion of the structure of the atom. Something you probably heard at some point in your high school career, but let's do it well and in one place and organized. So this is the end of chapter 1. This is the topics I want you to take away from chapter 1. There are other things mentioned, heat of vaporization, which I'll not ask you. This is too complicated a way of teaching chemistry to go into those details. But if you absorb these ideas, you'll be halfway done a successful first quiz, which will be on chapter 1 and chapters 2. So watch for the chapter 2 videos. Watch these 2 again and again, and ask me questions at Zoom or by email. So thank you, and welcome to 107, and welcome to an exciting term. Thanks for your time.